Hi everybody, I'm just going through this NCEA 2018 Waves paper, and this is question 3. I've had a request to answer question 3B, so I'll just show you what the question is. So it says, Clara wants to investigate the properties of a 0.400 meter length of solid steel rod. The bar is clamped rigidly at the center and the ends are free to vibrate. The rod is struck in such a way as to produce a fundamental longitudinal standing wave. So there it is. So I've drawn that there. And the first question is, show that the wavelength is 0.800 meters, and a diagram should be included in your answer. So the sort of wave that you're going to get through this, because it's clamped at the center, you're going to have a node there and you're going to have an antinode. This is almost like an open pipe. Okay, now the next part, this is where you needed help, but you just need to keep that in mind. So that one vibrates. Okay, then what happens is that this rod, let's go up. The next part is that this rod is clamped and put against a diaphragm, and the diaphragm is at one end of a closed plastic tube. So one end of the rod is attached to a diaphragm that can move freely inside a clear plastic tube. The plastic tube is closed at the opposite end, so that means it's like a closed pipe. So this is the open end with the diaphragm that can vibrate. Okay, and then when the steel rod is stuck, you get ridges over there. And the question was, the frequency of vibrations in the air tube is the same as the frequency of the vibrations in the steel rod. However, the wavelengths are not the same. Okay, explain why this is true for frequency but not for the wavelength. So that's okay. So when this rod is struck, the rod is going to move up and down, and the sound is traveling through the metal rod. Okay, and this one, so however, because it's touching the diaphragm is going to vibrate with the same frequency as the driver. Okay, so when the rod vibrates, it's going to cause the diaphragm to vibrate as well. So that's what's happening. So the frequencies are the same. However, the wavelength of the wave in the rod is going to be different from the wavelength of the wave over here, because what's actually happening is this is very fine powder. It's usually lycopodium powder, and it's there in some of the labs. And what's happening is the sound is vibrating through the air, so there's air in it. So sound is traveling through two different things. So it's traveling through the rod over here, but through the air over there. So the speed of sound is different in the rod and the air. And even though the frequency is the same, you have your formula V is equal to F lambda. Okay, so this is the same. But the sound is going to go faster to the rod because it goes faster through solid. So and it's going to go slower through the air. So when the speed decreases, your wavelength is going to decrease. So that's the reason. The main reason, it's traveling through two different medium. So even though the frequency is the same, the wavelength is going to be different. So I hope that made sense. So bye for now.